attending the good morning, everyone, and thanks for attending the webinar series of the ARMA Technical Committee on Induced Seismicity. We are very pleased today to have Tim Kneafsey and Martin Schoenball to present material regarding their findings of fracture network creation via hydraulic fracturing and shear stimulation. This is a very interesting project at the Mesoscale with great access to the results of the hydraulic stimulation. But before we start, we have a couple of announcements to make. Maybe as a reminder to point out that there will be a rock mechanics symposium, or the annual ARMA rock mechanics symposium will be held in Santa Fe, New Mexico, in person. For international audience, there is the ability to attend remotely. The details will be made available soon, if not already, at the ARMA website. And in conjunction with the symposium, they plan to have a workshop on induced seismicity. The title of the workshop is Best Practices for Induced Seismic Risk Assessment. And the plan is to have a number of key speakers to cover different aspects of induced seismicity in the context of carbon sequestration, geothermal, as well as petroleum reservoir development and waste isolation. The workshop will also be in person, and we urge everybody to attend because it promises to be a very exciting opportunity to discuss the developments to date, and also to see what's on the horizon in terms of better understanding and control of induced seismicity. With that, I hand it over back to Sean. He has some additional announcements to make.
Yeah, thanks, Ahmad. So June's going to be a busy month for induced seismicity workshops. So kind of complementing this ARMA-based workshop that's really kind of intended to be risk assessment across multiple industries, and you know, a good opportunity for experts from different industries to come together to talk about induced seismicity through ARMA. There's also early June 7th to 9th, will be the continuation of the SPE workshop series, again, on induced seismicity. This will be the 6th event in the series, and it's been a decade that the series has been running. It's really, again, complementary to the ARMA type workshop, but more focused on injection-induced seismicity, particularly hydrocarbon extraction aspects, hydraulic fracturing, saltwater disposal, kind of related. This series has been a fantastic dialogue between regulatory bodies, industry, academics, and committee's just getting the program together. We've got sort of keynote speakers listed here. So Mark Zovac, Aaron Velasco, and Jim Wright, Commissioner of the Railroad Commission, will be speaking to kick off the workshop. So again, complementary to that ARMA workshop, but focused on injection-induced seismicity. So more details to come. The registration's targeted to open next Monday, and either contact the SEG or myself if you want more information on that workshop. So with that, pass it over to Jens to talk about upcoming talks in this series.
Thanks, Sean. Good morning, everybody. Yes, upcoming talks will be the same time as they usually are in all cases. And so that's the first Friday of every month at 10 a.m. Central, with the exception, of course, the symposium that Sean just mentioned. Our next speaker will be Amanda Grieg. Note that that's changed. The day has changed. She went 1 week earlier than we've told you in the past, to the 1st of April, again, 10 a.m. Central here. She'll be talking about saltwater disposal induced seismicity in Northeast British Columbia. The following month, 6th of May, Mark Van Dyke from NIOSH will be talking about mining-induced seismicity in a coal mine, which, as I've mentioned before, is a departure from a lot of what we've the topics that we've had here before. We haven't talked much about mining-induced seismicity, although it is an important topic. So that'll be useful. And then finally, the 1st of July, Rebecca Harrington from Ruhr Universität Bochum will be speaking about using the seismic source properties of induced earthquakes and what that can tell you about lithological properties and source mechanisms and fault activation. Thanks.
Good morning, everyone, and thank you so much for joining us for another great webinar. I'm Mahdi Haddad at the Bureau of Economic Geology, and I welcome everyone to be here with us. We have a group of people from regulatory agencies and academic and industry in this webinar series. Almost 6% are from regulatory agencies from the attendees, 41% from academics, and 53% from the industry. We would like to expand this community, so please share the webinar invite with your colleagues who are interested in induced seismicity, or ask them if they want to be in the distribution list to be added to the distribution list by sending an email to us, me, Jens, or Sean, or Ahmed. And for better flow of this webinar, we ask everyone to be muted during the talk, and you can still submit your questions in the chat function of the Zoom meeting. And the questions should be sent to all of us as the host to be able to sort out the questions at the end to use the time more efficiently. And this Zoom meeting specifically is recorded after consultation with the presenters. The recordings that have been collected so far are uploaded in our Induced Seismicity Technical Committee YouTube channel. The link in this YouTube channel is in the invitation email. Please refer to that email for the direct link, and please subscribe to this channel to receive notifications for future uploads. And I see Peter is merely also raised hand for some announcement. I would like to give this chance to Peter to make the quick announcement, and otherwise we can proceed with the presentation. Peter?
Yes, hello everyone. This is just a very quick announcement to say that Sean's description of the workshop to be held in Santa Fe will precede the 56 US Rock Mechanics Geomechanics Symposium, and I just want to let you all know it will be held in person. We are having it on site and in person, and registration will be open within the next week or so. So I hope you all can come attend the workshops that Sean described, but also stay on for the symposium itself. And details are on the website. So I want to be very quick and just announce that.
Thank you so much. Okay, without further delay, let's invite Tim to share the screen and take over the stage. Tim.
Morning. It's really a pleasure and an honor to be here to give this presentation today. I'm going to talk basically about the EGS Collab project. I'll describe the project and what we're doing. Martin Schoenball will then talk about some incredibly interesting and fun data that we got, and his interpretation and the interpretation of others on that data. And then I'll finish up the presentation talking about experiment 2, which we're just getting started in the Collab project. I've put myself down as the author of this, but I'm really speaking for the EGS Collab team here. We're a large team. I'm really happy with this team. The interactions that we have, the discussions that we have are fascinating. For those of you, you might notice that there's empty space at the end of the slide. So, you know, if you want to contribute and you want to get involved, there's still more space on the slide. At the bottom of the slide, and the bottom of most of the slides, there's a couple of places you can go to get extra information about the EGS Collab project. If you do a Google Scholar search with the EGS Collab as the author, you'll get a listing of most of our papers and presentations. We have a wiki page, which is the center link on the bottom there. and our data is posted to the geothermal data repository and at the location that's shown there. You can also do a Google data set search, and it will point you towards the GDR and the data that we have there. We come from 10 national laboratories, 1 state laboratory, 2 companies. And again, there's more space on this slide if we need it. So by way of introduction, geothermal systems require, or to produce energy, it requires hot rock, some kind of permeability, and some working fluid. And when the working fluid or permeability are not available or adequate, and you add these missing ingredients, you've created an enhanced geothermal system, just very simply. If you're looking for hot rock in the US, you can see from the image on the left that there are a lot of very warm locations, very hot locations at 4.5 kilometers depth in the US. And that's becoming a depth that we hopefully are getting more and more comfortable at drilling to. The map on the right is showing the heat flux across the US. And so you're looking at places where more and more you might be able to produce energy from geothermal systems. However, they may not have the water or the permeability, and those might need to be added. So in permeability in these systems, I mean, there's natural permeability, and then there's stimulated permeability added to this natural permeability. And in oil and gas, fracturing has been done since the late 1940s, and some say since the late 1800s. In enhanced geothermal systems, the kind of permeability matters. We need to have an injection production connectivity. Let me see if I can find the, oops. So looking over here on the left, we have an injection well and we have some production wells, and we need to be able to connect our injection well and our production well with fractures. And the kind of permeability matters because we need approximately equal flow through each of these fracture sets to evenly extract the heat from the system. Shear stimulation is desired, and shear stimulation, looking at the cartoons on the bottom, you can open up a fracture in tension, and the 2 sides mirror each other. If you can shear the sides against each other, you've got a permeability that is likely to stay longer. There's of course chemistry and mechanics there. There have been many lab and simulation investigations of these processes, and many field deployments looking at hydraulic fracturing in the field. There have been a few field investigations where they're trying to get data back on these systems, but the validation and prediction of tools is pretty limited. So that's one of the goals in the EGS Collab project, is validation of prediction tools. So proppant use in EGS is considered, but geochemical reactions need to really strongly be considered there. In the EGS Collab project, we recognize that deploying EGS requires de-risking by gaining additional knowledge to create and sustain reservoirs. Field tests like EGS Collab and Forge are needed to validate existing state-of-the-art numerical simulators so we can extend the knowledge we have. The EGS Collab project is a collaborative experiment, model comparison project, and we're to compare and validate reservoir model predictions with 10-meter scale field experiment data. We're to do in-depth fracture characterization, to perform, to well perform and monitor experiments, collecting high quality comprehensive data, and to elucidate the basic relationship between permeability enhancement and stress, seismicity, and other parameters, to improve the tools for Forge and EGS, and to face and address problems that will occur. So that's a pretty tall list of things that we're trying to do there. We envision the Collab project as 3 experiments. Experiment 1 was intended to investigate hydraulic fracturing, and that was done at the Sanford Underground Research Facility at 1.5 kilometers depth, and that field work is complete. So that's at this location that I'm pointing to here. Experiment 2 is designed to investigate shear stimulation, also at the Sanford Underground Research Facility at 1.25 kilometer depth, and that is initiating, and I'll talk about that a little bit at the end of the presentation. And then experiment 3 allows us some flexibility in examining the stimulation techniques that we're using, and that is likely to occur immediately following experiment 2. And each experiment consists of multiple stimulations. Let me see if I can move this out of the way here. So multiple stimulations, characterizations of flow, tracer and heat transfer behavior. Pre and post-test simulations are required for each. So we have to compare our stimulations and our stimulations and our flow tests. And I'll be talking, like I said, about experiments 1 and 2. The experiment layouts and instrumentation, we are required to do well-characterized and well-instrumented experiments. Experiment 1 is shown in the upper left here. This brown line is the drift or mine tunnel at 1.5 kilometer depth. From there, we drilled an injection borehole shown in green, a production borehole shown in red, 6 monitoring boreholes, which are shown in yellow, and these have grouted in instrumentation. The 5 holes in orange that are shown here are vertical holes that were part of a test called the Kismet test, where people were trying to assess the stress in the rock at this level. So the local stress measurements we've done, or local measurements, borehole, we've done optic and acoustic televiewer, full waveform seismic, electromagnetic, gamma, temperature, fluid conductivity. Further looking at the test block, which is in between all of the monitoring boreholes, P and S wave characterization with mobile and grouted sensors, extended hydrologic characterizations, electrical resistance tomography for baseline and flow. We've done numerous tests and examinations on the core, and they're listed here. I'm not going to read them all to you. In our tests, we do acoustic emissions, continuous active source seismic monitoring, micro earthquake, electrical resistance tomography. We look at temperature by distributed temperature sensing and thermistors, strain by distributed strain, and direct 3D fracture displacement using the SimFit tool. So in experiment 1, this is a cartoon showing either where measurements are made or where an instrument is set. So it's pretty well instrumented. Experiment 2 looks very similar in the setup to experiment 1. In experiment 2, this blue line here is our drift or tunnel. The yellow lines are monitoring wells with these 4 to the right have grouted in instrumentation. The injection hole is shown in green, production holes in red, and this is a kind of a free well that we can either use as a monitoring well or production well. And here's a picture of people putting a packer system into one of the wells at experiment 1. Martin Schoenball, Hunter Knox, and Chris Strickland pushing the packer in. So there's a lot of people who've contributed to this work, and a lot of people were required to get any of these measurements made. One of our goals was to engage a large community of researchers and to have adaptive control of our test. And something you'll see more of in the presentation when Martin talks is our MEQs. This is the panel that we were looking at live when our tests were going on. So everyone was able to monitor at least 6 of the parameters full time. We're locating our MEQs typically within tens of seconds of when they were detected. And so we had a really good idea of what was going on in our system. One of our tests went 30 days, 24/7 Zoom call. So whenever we needed somebody, there was someone online who could respond to the system, respond to what needed to be done. And so with that, we gained some adaptive control of our system. We also took our data and immediately appended the metadata to it. So one could look at what's happening in the data and what was adjusted or changed in the system to get an idea of what might have caused that. It's a photograph of the bottom left of our experiment 1 site. It's pretty much a Cadillac of an underground working environment, lots of light, big airy environment. telephone, internet, water, air. It's very nice. And then during a stimulation, looking at the data underground, a lot of us were looking from above ground, but underground, just watching what's happening. So there were a lot of interesting things that occurred here. And one of the things that we noticed is that we might have a thermoelastic effect. We measured temperature from our drift, our tunnel, out into the rock, and using numerical modeling extended the temperature gradient that we measured. The drift is cooler than the ambient rock because it's been ventilated for several decades. And so the drift is about 20 degrees C, and the host rock in this region is about 35. So we have a temperature gradient there. The temperature gradient induces a stress gradient. And this stress gradient that's induced, then when we do our stimulation, we hypothesized that it would draw the hydraulic fracture towards the drift. And so this was our hypothesis. This is numerical simulation based on a heterogeneous distribution, stress distribution, but based on the temperature distribution that we have here. So the hypothesis was that the fracture would go towards the drift. And then in looking at where the fracture actually grew, this was the stimulation location. I see I don't have the red dot in the far right panel shows the stimulation location, and the flashing arrow shows the direction of the fracture that formed, which is pretty much the direction we thought it would go, and it moved towards the drift. In all fairness, there are a lot of other induced fracture planes that are shown here from other stimulations, and there's a lot of interpretation. Martin will talk about a lot of this as well. But this was a validation of the concept from our thermoelastic effect that we had. We did a number of major experiments and tests in experiment 1. We did stimulations, multiple stimulations at 3 intervals. We established hydraulic connection between the wells. We stimulated a large fracture system and created new hydraulic fractures. Some of this was something we didn't really want to happen. If you're looking at the panel on the upper right, you can see let me get my marker again. So we were stimulating at this location here, and we had a stimulation through the natural fracture system that moved in this direction on this plane rather than towards the drift, which is where we initially thought it would go. So we were able to stimulate a natural fracture system as well. This took water off of the system that we were hoping to make measurements from. We also did a year-long cold water injection test, and we got 90% water recovery there. So we flowed water towards our well, and then we also had to collect at a couple other locations. All of these tests were subjected to continuous geophysical monitoring and extensive analysis aided by near real-time numerical modeling. The tests were performed with Zoom calls to allow observation and adaptive control. I just want to bring up a few points. These were stimulations that were done that we call the 164-foot notch. We had a couple of notches that we etched into the borehole to do our stimulations from to try to direct the initiation of the fracture. So in this set of tests, we did a small stimulation to drive to a conceptual 1.5 meter fracture. We went on to a 5 meter fracture, conceptually drive through to the production well. And then we did a number of flow tests. And so the volumes we used are shown here. So relatively small volumes and relatively small rates too. The first couple of these stimulations were done with a laboratory pump. So we got up to 400 mils per minute. We did a lot of our flow tests at 400 mils per minute. One of the things that I want you to notice in this slide, however, is the propagation pressure. Looking at these numbers, 36, 37, 3,800 PSI, instantaneous shut-in pressures, kind of along the same order of magnitude, 3,700 PSI. So this is important because I'm going to show you some of the flow test data in just a second. So I just want you to have that number in your head when you're looking at the flow test data. So this is flow test data, and there's a lot that I'm showing here. In the top panel, we have injection pressure and injection rate. So injection pressure shown on the left here, injection rate on the right. So this is at 400 mils per minute, the green line that's showing here. Injection pressure, so I just told you to look at that number, 3,700 PSI. Injection pressures are all on the order of 4,000 to 4,500 PSI. This is second panel is a blow up of panel one. So you can see the pressures a little bit more clearly. Collection flow rates at different locations are shown in panel three. And the thing to take from this collection rates is that there are multiple locations where water flowed to, and they changed over time. And some of these things we could explain, and some of them we couldn't. So the first thing I want to point out is what's highlighted here in these red ellipses. Whenever our pump went down, or whenever we turned the pump down, even for tens of seconds, 30 seconds, for example, and then we started flowing again at the same flow rate. So we're injecting here at 400 mils per minute. The pump went down for 30 seconds, we turn it back on. All of a sudden, we can pump the same flow rate at 200 PSI less than we were injecting before. And we see that happen every time the pump went down or we had to shut the pump off for some reason or other. We got this change in flow rate. And so it's an enhancement in permeability, if you will. And then it's followed by a decrease in permeability over time. And then the next time it happens, we get an increase in permeability. We've had a number of possible explanations. One is geochemical. We're getting some dissolution precipitation going on. We're getting fluffy precipitates. And then when we shut the pump off for a second, the pressure goes down, the precipitates get squished, and then we turn it back on and they're not in the way so much. Another is biological, kind of along the same argument. We have fluffy biology in there. Shut off the pump, the fracture closes and squishes the biology, turn it back on, and we have a higher flow rate. And the other is a thermoelastic, excuse me, a poroelastic effect. We have this pressure that's exerted on the walls of the fracture holding it open. We stop flowing, the pressure in the rock decreases a little bit, we start flowing again, and we have a little bit more permeability there. Another thing I'd like you to look at is when we went from our ambient water injection, which is shown in the blue here, to our chilled water injection. Well, our pump went down again. So we had our normal decrease in pressure, so increase in permeability. But then instead of the pressure increasing immediately, we have the pressure decreasing and continuing to decrease for some time before it changes. And so what's likely happening there is a thermoelastic effect. We have the chilled water chilling the rock right near the borehole in the fracture, opening up the fracture a bit. And so we get an increase in permeability there. Every time we had a temperature change, for example, our chiller went out a couple of times. Looking at the green ellipses on the panel 4, the chiller went out. You can see that there is an immediate change and a noticeable change in what our perceived permeability is. So we have a thermoelastic effect going on there that is shown. Martin, do you want to take over now? I'll stop sharing.
That sounds good. I can take the screen again. This one. Can you see my presentation?
Not yet.
Not yet. It worked before.
So Tim, it looks like he's stopped sharing, and I guess Martin, you're just having a hard time sharing. Is it the...
I don't know. You can't see my screen. I thought it shared.
No, we can't see your screen, and I have stopped.
I'm sorry. I don't know what's going on. One second.
I have a copy of that. If you want, I can share it.
Just give me another second.
Oh, sure.
Let's do this. Oh, there you go. Right, now you should see my screen.
It's coming up. Yeah, we can see it now.
Right, so I had the pleasure of working in this project as the lead on the microseismic monitoring, and it was certainly one of the coolest projects I've ever been working on. I now changed gears and I moved to Nagra 1.5 years ago in Switzerland, looking at nuclear waste disposal. But let's keep looking at Collab. This is not going on. There we go. All right, so Tim already showed you a glimpse of the monitoring systems that we put in place. Here is a more detailed view of the seismic acquisition systems. So we have our 6 monitoring boreholes here in black, and they were instrumented, among other things, with 2 hydrophone strings here shown in red. Each of them had 12 hydrophones. We have 18 3-component accelerometers, the blue triangles here. We also had 4 geophones that were installed into some shallow wells that were drilled directly from a drift. They are not shown here since we didn't use those data. And all sensors are grounded in these boreholes, including the hydrophones. We were quite excited to see that these hydrophones actually work also grounded in. All of these sensors were connected to 2 recording systems. One system that was recording at 4 kilohertz continuously. As I show you in the next slide, the frequency content of the signals that we were interested in was quite beyond that. So basically, we didn't get any useful signals out of these recordings. But we also had 100 kilohertz continuous recording on 64 channels, which included the hydrophones and the 12 of the accelerometers. So the data rate that we got with this kind of system was quite significant. So I want to just tell you about the 1.6 gigabytes that we were handling per minute. We were archiving those data on 8 terabyte external drives, which each covers about 4 days of recording. And we were recording for continuously for well over a year. The data was handled using a Python stack based on the OpsPy package, which allowed us some near real-time processing on a not too big 8-core workstation. Tim mentioned that we had like tens of seconds of delay. However, I have to admit that during the active times, during the stimulations, when we had hundreds of events, performance slowed down quite significantly, and we did get a backlog of maybe half an hour in some extreme cases. After the automatic processing, I performed a manual refinement of the picks for the PNS wave arrivals. And then I used a modified version of hypo-inverse to do the location. One big issue that we had to deal with was that the accelerometers work basically in the resonance range for the signals that we are recording here. So on this panel, I show you the frequency response of the hydrophones, which is actually pretty good up to high frequencies. But the accelerometers here, they get into resonance at around 10 kilohertz for the X component and a little bit higher frequencies for the Y and Z component. And if we look at the spectrograms of 2 events here, or actually it's just one event, I believe, we see that on the accelerometers, we have this very strong frequency at a very strong resonance at high frequency, which is absent in the hydrophone data. So this was certainly providing some challenge in the processing. Let's look at some closer details of the simulations. The very first simulation where we injected at about 200 milliliters per minute lasted about 10 minutes. This test was designed to create a fracture of a nominal diameter of 1.5 meter. Obviously, we did not create a penny-shaped fracture, and so we recorded seismicity significantly further away. After this 10-minute injection, we performed a shut-in overnight and continued operation the next day, where we injected more fluid at a slightly higher rate, up to 400 milliliters per minute. And this test was designed to drive the fracture to a 5-meter radius diameter. Obviously, here we again had we extended seismicity further away, which was, amongst other things, related to the one-sided direction of this fracture propagation. Since our target was to create a flowing system with our production borehole, we continued injection the next day, but now at much higher rates, up to more than 4 liters per minute. And we were able to connect to the production well, creating lots of seismicity here. So you see the seismicity is many more events. And then later on, we performed a few flow tests the next following day, again at very high flow rates for our scale, at least high flow rates, and created some seismicity. The colors here of these events, I should say, relate to the fractures or the features that they were located on. So you can see, for instance, that at this last flow test, we have this one feature here, which was active only then and has not been observed before. For most of the other fractures, though, we see that they are active during most of those tests. So we had several features active at one time, of course. If we look closer at this drive to 5-meter test, and plot the distance over time of events relative to the injection point, we see this fairly expected square root of time behavior. We can plot this also in a 3D plot here and look at the time. And then we see that seismicity grows upward and then makes a little bit of a turn. Interestingly, we have this little arc here, which corresponds to one of our boreholes, borehole OT. And you can sort of glimpse through the colors when it might have hit this borehole. But we also can corroborate this information from our temperature sensing. So as you saw, all the monitoring boreholes were equipped with fibers for temperature, strain, and acoustic sensing. And here we see that we recorded temperature anomaly, a positive temperature anomaly, starting at around 1930, which was when this fracture intersected this borehole. The temperature anomaly can be related to a pressure decrease of water in the borehole as it squirts in the borehole. And Tim has shown you some animations of how this might have looked like also in this borehole. So what's interesting is that we had this one-sided fracture growth, which was expected from also prior simulations. We had a fracture growing in a direction that is consistent with the orientation that we would expect from a hydraulic fracture parallel to the SH max direction. But we also have some fracture trends that are not compatible with this interpretation, so which must have activated by shear. And here is a 3D view of the seismicity. So we have this shear feature here, and then also a hydraulic fracture, or maybe actually a set of hydraulic fractures. If you look closely, you may be able to see that there are like subparallel fractures, hydraulic fractures, or something that's almost like a conjugate fracture that still has a similar orientation. We performed additional simulations at other locations. Here, this is some stimulations that we performed at the 142 notch. The seismicity response at this location is actually quite different. We have some seismicity that is at least in line with the interpretation of a hydraulic fracture, so in this sort of east-west trend here. But most of the activity was actually correlated with a southeast northwest trending feature, and even this almost north-south feature here. What's well, was fortunate for me, but quite unfortunate for the experiment, is we fractured, in this test, we fractured all of our boreholes, as we can see here from the DTS. So in each of the boreholes, we see these temperature anomalies, very localized, indicating where the fracture intersected these boreholes. So this was very useful information to corroborate the seismic results. And for instance, we can see that this feature here actually fractured into this borehole at quite a far location away from the seismicity. So we didn't record seismicity up to here, but we certainly got a fracture hit at that borehole. And there's the 3D view. So here's an overview of all the seismicity that we recorded in stimulating the 3 zones. This is the 164 zone here in red, the 142 zone in yellow, and then we did another test which I didn't talk about here in blue, which activated some very shallow dipping fractures, and then also ruptured a borehole, fractured this borehole here quite far away from at least located seismicity. And these diamonds here, they mark locations that we recorded either through the DTS or also through direct observations in the production borehole here in red, where a fracture intersected these boreholes. And they are pretty much in line with the seismic locations. Overall, we identified about 10 distinct fault planes just from the hypocenters of the micro earthquakes. And as I said, the interception points of these fractures are consistent with the DTS and with the in situ conductivity measurements which we performed in the production borehole. We can plot these identified fractures here in this diagram of the slip tendency, which gives us already some ideas of what these fractures might be. We can also compare these fractures with the borehole image logs where we and the core, where we identified foliation planes on the right-hand side here, and then all the other fractures on the left-hand side in these two stereo plots. And so this helps us also to understand the mechanism for the fractures that we mapped through the MEQs. We have a series of hydraulic fractures here, up here, which corresponds to this fracture, and then a number of hydraulic fractures which land down here. This yellow zone here, which was very diffuse, and then of course what we activated in the first injection test or stimulation test. But we also activated some fractures that are very shallow dipping, which were these two fractures here we activated in the last stimulations, and then also some features which seem to correlate best with, let's call it rock fabric features. There was a question already about the distributed acoustic sensing, so I'm happy to have some really exciting results from this to show as well. Along these monitoring boreholes, we had also fiber optics that were interrogated with a Silixa IDAS unit. We didn't record any useful signals from the microseismics or from the active seismics, but looking at the low frequency content in this data, by integrating the signal for the low frequency response, we were able to get some pretty exciting insights here. And there we are using the ability of DAS to record extremely small strains. And so this is a movie of one of the stimulations where we reopen this fracture here. And I want to show you this. So on the bottom, right-hand side, you see how we are stimulating this. We're injecting it, opening up the fracture only now. And you see some extension and compression happening in these boreholes. And then also the recorded seismicity here in green. aligns pretty nicely with the deformation pattern that we observe. What's really interesting, and this is, well, I can show this, give this movie a little bit more time. What's really interesting is that after the fracture closes, after we cease injection, the deformation still continues for quite some time. And so we see the closing of this fracture and can follow it over a very long time frame, as I show you in this plot. So here, just to orient yourself, we have on the x-axis time over 5 days. And then each of these panels gives us one borehole. This is the borehole OT, which was fractured at the very beginning of the boreholes. And then we have the other boreholes here, where we, in this period, did not create any fractures. And so you can see just a pore-elastic response here in these boreholes, which were not fractured. We have this strong response in borehole OT, where we see the fracture approaching, then actually the fracture hit, reopening the fracture, and then we see this transient behavior as the fracture is closing. We also noticed something in this borehole OB, which looks like a fracturing to me. So this is kind of a similar pattern that we see here, but where seismicity was not, or we didn't know about this fracturing from any other means. We can compare this also with distributed strain sensing. So this is the third fiber-based method that we're using here. So this is a snapshot from the borehole OT. We do see the strain as well, but the signal to noise ratio in this data is much worse, and DAS really gives us a lot more resolution there, at least in amplitude. Lastly, I would briefly mention the active seismics. In the chat, I already responded to a question referring to velocity models and velocity monitoring. And so what we used active sources, 20 active sources that were running in velocity epoch basically every 15 minutes. And after we gained some confidence, we ran these tests also during the injection intervals, injection periods, I should say. And here is the velocity changes that we recorded at a specific point using this technology. And you can see that as the fracture is opening, we have a decrease in velocity and then a recovery as well. And with that, I want to point you to some papers where you can read up on this. Champing Chai did a very interesting study using this the seismicity that I showed here and applied a neural network and machine learning. Peng-Cheng Fu and others did some more interesting analyses and interpretation of the fracture observations. Yves Guglielmi and others detailed on the application of the SimFib, and then the stuff that I showed here is presented in this paper. And with that, I want to hand it back to Tim. Tim, you're still muted.
Thank you. I just want to talk for a minute about experiment 2, and then we'll have a few minutes for questions. So experiment 2, we're targeting shear stimulation, and we're doing it on the 4100 level, or 1.25 km depth at SURF in amphibolite. The experiment 1 was done in phyllite. We have 5 fracture sets that we have to consider in the design. In our tests, none of them are taking water. We've drilled 2 characterization boreholes, 9 test and monitoring boreholes. We've done 8 stress tests with the SimFip tool and 10 without. We have other stress indications being evaluated. There's a team from Respec that's making inferences on stress using thermal techniques. So we're able to watch what they're doing. They're able to watch what we're doing. We've designed many different test bed configurations and settled on one. And our test bed construction is complete. Below the rock at the 4100 level, we go through about 70 feet of amphibolite. Then there's a thin rhyolite layer, another 30 feet or so of amphibolite, then a thick rhyolite layer, and beneath that amphibolite. The instantaneous shut-in pressures through these zones vary significantly, with moderate values above the thick rhyolite, low values in the thick rhyolite, and high values below. So our whole test is designed to be in this upper amphibolite. The experiment 2 test bed is shown here. This is, I think, a really impressive setup. We're just the plumbing that we have to control the flow in and out of our test boreholes. This is at we call site B. This is at the injection production and a couple of monitoring wells. Here we have site A further up the drift at the alcove, and site C also further up the drift with the monitoring boreholes. But this is just an impressive setup that the team has come up with to perform this test. The geophysical monitoring sensor locations, this is a plan view. Site A off of the battery alcove, a couple of wells off of there with seismic sources, seismic receivers. You can see the key down in the lower center portion of the slide. The red well is the injection well here. There are 3 open wells there, and then we have an open monitoring well, which is blue, and you can see where the tools are all set up there. We will be using the SimFit tool again to monitor strain across a fracture when we do stimulation, so that we can see if we get any shear. And then we have a tool that's called a DORSA, which is similar to the SimFit tool, but it will be applied in the uppermost gray well that's shown here. It's the sort of the orange-brown tool shown here, and it monitors strain as well, based on the same concept as the SimFit. The boreholes, the monitoring configuration is shown here. We have an ERT electrode, electrical resistance tomography electrodes on the outside of a PVC shroud, which is then put into the borehole. Our distributed temperature sensing is on the outside of the shroud, and we can put our seismic string on the inside of the shroud, and this whole thing is grouted in to the assembly. Stimulation plans, so we've targeted the highest shear to normal stress fractures that we can find. And we have a couple of different models of stress. We will isolate these with a straddle packer, and then we'll apply a sequence of pressures and over certain durations to see if we can get water into the fractures, see if we can make the shear stimulation occur, and observe for changes in permeability. If we can't make any shear stimulations occur, then we will proceed with a hydraulic stimulation, trying to shear stimulate fractures that are naturally present. As I mentioned, we have project information sources. We have the wiki. The address is shown in the upper left here. You can find our data it's either on the GDR, or you can find it using Google Datasets. And using Google Scholar, you can find most of the papers and presentations that we have available, and you can take a look at them there. There's a veritable mountain of information in this project, and the data are available, and we hope that you use them. We have strived to provide good metadata. There's a lot of papers that help provide some of this metadata. We really want you to look at the data, and we really want you to use it. We've worked really hard to create a good data set that's useful to the community. So this concludes our presentation. If there's time for questions, be happy to take them.
That was an excellent presentation, Tim, Martin. Great project and great overview of lot of obviously impactful learnings. And thanks to both of you answering. There's been a number of questions on the chat, but I think between the two, you're able to respond to a number of them. There is a follow-up from Pierre-François Roux asking about going back to the DSS, DAS. So the distributed strain looks, as you pointed out, noisy. Do you have plans to kind of rectify that noise for the next phase, or any additional comments on the noise source there?
I don't think this is just the limit of the method in this case. This was a light test DSS unit, and we believe it's just what this instrument is capable of doing at this point.
I don't know what instrument we're using in experiment 2. A lot of thought has gone into this. If you send me an email, I can fire it off to Chet Hop or Veronica Rodriguez Trabaldos or Jonathan Aho Franklin. They can give you a very detailed answer to that question.
And I guess a question for me on kind of a similar note. So Tim, at the start, you talked about that kind of conceptual model of a fracture dilating and then shearing afterwards. And if you put all the diagnostics together, the kind of the strain observations that you do have and the microseismic response, are you seeing that in sort of a sequence, dilation followed by shear?
Trying to think. We have a graduate student at Texas A&M who is taking a very detailed look at that right now, and he has written a paper, and we're in the process of evaluating the paper and getting it out. And I wish I could answer. I just can't remember what I can't remember what the conclusion was, but I could even send you a draft of the paper if you're interested.
I would be able to appreciate that for sure. Thanks, Tim. And so we're pretty much to the end of the formal time, and appreciate kind of the presenters' availability to stick around for a few minutes if they can for more informal Q&A. But I'd like to take the opportunity on behalf of ARMA and the ARMA Induced Seismicity Technical Committee to thank both Tim and Martin for the excellent presentation here. Excellent material, and just looking at the number of questions in the chat obviously generated a lot of interest. And just a reminder to the participants, the next webinar will be April 1st. Amanda Gregg, Amanda's a colleague of mine at Ovintiv, so she'll be presenting on a really interesting case study, managing saltwater disposal injection induced seismicity in British Columbia. So watch for the invitation to that. Again, April 1st is at 10 Central is the time of that talk. Thank you, everyone. And again, thank you to the presenters. So guys, thanks for also agreeing to kind of have more of an informal kind of discussion here. So usually at this point, we invite if there's anyone that wants to unmute and ask questions, and I'll maybe take again the opportunity to kind of kick it off. I guess a question for Martin. I don't think I heard, do you have magnitude estimates for the events? What sort of moment magnitude range do you think you're detecting?
Yeah, we don't have accurate moment magnitudes because of the sensor response issues. We have guesstimates based on just the characteristics of the waveforms, though, which would be in the -2 range for the largest.
We will be hopefully doing better in experiment 2. We've got some different sensors that we'll be using, and a different spectrum of sensors that we're using.
It's good to hear.
Hi, all. I just want to say I have to run to another meeting now. Thank you. That was very informative. I left a question that maybe we can talk about a different time. Thanks again.
Bye, Jens.
Yes.
So Tim, when are the next simulations happening?
Let's see, 3 weeks. And anyone who wants to participate in the week-long live meeting, if you wish, send me an email and we'll add you to the Zoom call list, and you can watch the data, you can participate, you can chime in. The last time it was, I think, fantastic that we had the participation that we had and got good information, good thoughts, and we're able to respond very quickly to any stimuli.
I would certainly be happy to get that link.
I see a question by L. Steele. How do we express an interest in participating in the overall project?
You can send me an email. And I would be happy to. I mean, we have a couple of things that happen regularly. We have a field call that happens every week. We have a modeling and science call that happens every other week. That's probably the best one for people to attend if they wish. But the data that we have are available. We try to make them available as soon as possible. It's not possible to get them out immediately sometimes, but we try to make the data available and we try to describe it as well as we can, so that people can use the data. And DOE has pressed hard to get us to make it so that it's useful to everybody. And we've pressed hard to make that happen as well.
Great, thank you. So I'm not sure if this question is addressed by Farhang or Sadan. Are there rock velocity measurements before and after fracturing?
Yes, this is the active seismics, and which I showed in my last slide, and this is, I believe, the data should be available as well on the GDR.
Mm-hmm.
Yeah, there's a Jonathan Franklin has a really interesting slide. Maybe I have it here. Let me double check. And it shows the measurement of the, oh no, I don't have it in this slide deck, sorry. It shows the chasm data during the stimulation, and it shows the changes in velocity over a plane before, during, and after the stimulation. It's really a fantastic data set. I'm sorry, I don't have it in this slide deck, however.
I did have it in my slide, but then I deleted it for the sake of time. I can share that here. Let me see if I can share my screen a little bit better this time. I don't like Zoom anymore. There we go. Sorry, this is. Can you see my? Yes, there we go. So what we had is what we call the continuous active source seismic monitoring CASM. And we had the hydrophone array here in the blue well, and then CASM sources, so active seismic sources. There are piezo sources. 20 of them in the whole test bed, and we had 5 in this particular well where we basically have this one imaging plane that I can show you here. And on the right-hand side, there's a movie from one of the stimulations. I believe it's the same movie or the same stimulation that I showed in DAS. And you can see as we pressurize the system, we are opening up the fracture, and then we are decreasing velocity. And then after the fracture is closing, we can see how the velocity changes decrease slowly as the fracture is closing, similar to what we've seen in the DAS. And we can also see how this compares to the active to the passive seismic. So here this is overlain with the microseismic event, so you can see that there's a pretty good correlation of the velocity changes seen with the location of the seismic events.
And it also shows with the DTS at the top left of that panel where the fracture intersected the well OT.
Yeah.
So it's a nice correlation between all three.
This might be a question for you, looking at the question Jens put in chat. So I think you mentioned looking at more of the critically stressed fractures for preferential shear slip, but is there any thought of kind of targeting some of the fracture sets that are maybe not preferentially oriented, lower normal or shear stress?
So the well that we are going to be stimulating, we call it TC. It's a test well in the center, so TC. And there's about 90 feet of well in there that's in the well monitored region. I think it's 90. The region of the SimFit tool is about, it might only be 70 feet. It's about 7 feet in the SimFit tool. So we are going to actually try to stimulate every portion of that well. We have a stimulation protocol that we're going to go through, and we're going to target shear stimulation in every one of those. And if we cannot shear stimulate, then we're going to go to a hydraulic fracturing, and we have a region that we are targeting for hydraulic fracturing. So we've got a protocol that's set up, but we will be looking at fracture sets, all of those fracture sets, and looking at what happens there. And we'll be using the SimFip. If we do get stimulation, we'll be able to identify which fracture set we are stimulating.
That sounds like a really impressive experimental plan.
Hopefully the experiment comes out impressive.
Yeah. All right, I think there's still a few people on. If anybody's got a question, feel free to unmute and jump in here.
So I have a question. Recently, I was informed about a type of fiber optic that can monitor, for example, pH or chemistry of the fluid. For example, in geothermal resources, you may need to do that. Is there any plan in this project to install that and test it? Because if the application is geothermal, the positional environment in geothermal may be very complex that needs this capability to monitor that from the geochemical point of view.
So the answer to your question is no. We don't plan on doing that. It would be possible to do that in our open monitoring wells around the stimulated well. The other ones are grouted in, and I think that they would just detect the chemistry of the grout. And so, you know, if someone is interested in doing that and they have the equipment, we might be able to implement it. We would have to do it very quickly if that's the case, however. But we do not have the equipment or the budget to do that at this point.
Mm-hmm.
It's a great idea.
Yeah. Thank you.
All right, well, we know it's late in Geneva for Martin, so why don't we go ahead and kind of wrap this up unless anybody has any last sort of questions. But again, Tim, Martin, just thanks so much for the presentation. Really, Tim, I caught your presentation to the ARMA fracture community, and nice complementary information to what you presented today, but just a fantastic wealth of information that you've collected here. So thank you for sharing it.
Well, thank you. And I want to thank Martin for, I mean, presenting. I think that some of the data that Martin was presenting and his interpretation are just key. And thank you for presenting the information, Martin. I mean, I learned so much from you, and I want to keep learning so much from you. So I really appreciate your presentation.
Thanks. Thanks for the opportunity.
Thank you for both of you to present for us. Thank you so much.
You're welcome. Y'all have a good day.
Thank you.
You too. Thank you, everyone.
Bye-bye.